Ladies and gentlemen, today I'll be explaining why groups are so important. In this second lesson of group theory, I'll be passing over 4 examples of groups. Now you may ask, how are these examples useful or even related to real life? And I will tell you, you should probably have a look at the clock that I put over there. It was not put there by mistake, and it was not put there accidentally. This is actually one of the examples that I'm about to show with you. I'm about to share with you the examples of the integers, first of all, and then afterwards I will give you the integers modulo n, and then afterwards I'll give you the integers which are coprime to n, and lastly, the direct product of two groups. Let us start with the first example. The first set of numbers that mankind has known is the set of counting numbers. We have counted starting 1, 2, 3, 4, and so on. So if I write that down here, we find a list of numbers going up to infinity. Now, we know that these are not all the numbers that there are, but these are the first numbers we've invented. But what about the other numbers? We know that if we add 2 to 3, we get 5. If we add 2 to 4, we get 6. But how do we go to 0? How do we go to negative numbers? There are no two positive numbers that add up together and get a negative number. Well, for that, we need to include what we call the identity element and the inverses. In the first lesson, we have defined each of these terms, and for here, we will give the terms themselves. So for the identity element, it would simply be 0. Simply being because if you add 0 to any of the elements in the set, you will obtain that same element. So, for example, 0 plus 5 gives 5. It does not change the element 5. So that is the identity element. And the inverses of each of the numbers, for example, the inverse of the number 1 is -1. And why is that? Because if you add -1 to 1, you obtain the identity element. If you add -2 to 2, you obtain the identity element. So by definition, these are the inverses. Together, the set of integers with the operation addition makes a group. So that's great. We have a group. So the operation is addition, the identity is 0, and the inverses are the additive inverses, which is the negative of the element. So that is well and good. Let us move on to the next example. If you are familiar with modular arithmetic, this part may seem a little boring to you. But I found that this first example has hooked me line and sinker to what modular arithmetic really is. Imagine a clock. You don't need to imagine that. There are clocks everywhere. You use them all the time to tell the time, of course. But have you really thought about what it means to really go in a circle, in a cycle, to never really escape the 12 numbers you see in front of you? Well, I'm here to tell you that mathematics has formalized this in what we call Z and Z, the integers modulo n. In this example of a clock, the integers are modulo 12, because we start at 0, which is 12 o'clock midnight. We go 1, 2, 3, all the way back up to 12. But we don't really say 13, at least not in 12-hour format. We go back to the number 12 or the number 0. So we say it's 0 hours. And if we add and we keep adding and we go back to 12, we repeat the cycle over and over again. So for example, let us add 3 plus 9. So 3 plus 9 normally gives 12, right? However, if we implement it in this new universe of small numbers up to 12, we will add what we call a bar on top of each of these numbers. And this number 12 bar is equivalent to saying 0 bar, because we're right back up where we started. So this system effectively reduces all of the numbers that there are modulo 12. For example, could you tell me what modulo 15 is? What is that equivalent to? Well, to figure that out, we need to keep subtracting 12 until we end up with a number that is strictly between 0 and 12, including 0, of course. So 15 minus 12 gives 3, and 3 is the smallest number there is in this universe. So 15 is congruent to 3. This is modulo 12. And therefore, this is a new system, a new set of numbers, which is simply put the set of numbers 0 bar, 1 bar, 2 bar, all the way up to 11 bar. And 12 bar is just 0 bar again. Now, is this a group? Yes. Yes, it is. It is a group, absolutely, with addition. You add two numbers, you get a new number that is modulo 12, just as I showed you now. Now, what about the identity? Well, we need to think about what element that if you add it to any of the other elements changes nothing. That is just 0 bar. 0 bar is the identity. It respects totally the same rules as above in the integers. What about the inverses? Well, what element that you added to any of the elements, you get back 0 bar. Let's think, for example, 3. 3 plus what element gives you back 0? Well, you could say minus 3 bar, right? Which is totally valid, because minus 3 bar plus 3 bar, you can in fact combine the two numbers and put the bar on top of their sum, and that gives you 0 bar. Now you would tell me, but what if I don't choose minus 3 bar? What if I choose 9 bar? Because as we've seen before, 3 bar plus 9 bar gives you 0 bar. And I tell you, well, that's the same element. 9 bar is congruent to minus 3 bar. So is there a way to know if two numbers are congruent? Absolutely. If you take 9 minus minus 3, so if you take the difference and you divide it by 12, you get an integer. So A is congruent to B mod 12 if 12 is a divisor of the difference A minus B. So this notation means that 12 is a divisor of A minus B. Great. That is now minus A bar. We found our operation, identity, and an inverse. And therefore, this very real-life application is in fact a group. Let us move on to the integers modulo n, which are coprime to n this time. So, for example, let's take the same normal clock system. So z, 12z. But this time, we will only take the elements that are coprime to 12. So we will see which elements are coprime to 12. Coprime meaning that they share no other divisors except 1. So 1 is coprime to 12. 2 is not coprime to 12 because they share a divisor, which is 2. 3 is not coprime to 12 for the same reason. 4 is not. 5 is coprime to 12. 6 is not coprime to 12 because they share common divisors, which are 2 and 3, and 6. 7 is coprime. 8 is not. 9 is not coprime to 12 because they share 3. 10 is not. They share 2. 11 is. So we end up with 4 elements in the clock system which are coprime to 12. So I will be listing them here. 1, 5, 7, and 11. Now let's think about what operation we could use. Well, if you think about the operation of addition, does that really make sense? Let's say it does. Let's say we have the operation addition in this set, right? Then tell me, please, what element in this set that if you add it to all the other elements, you change nothing? I don't seem to find a 0 in this set. Otherwise, my problem would be solved, right? 0 plus anything gives that same number. However, here I don't have it. So maybe addition is not the right operation. Maybe it is multiplication. Maybe if I multiply the element 1 bar with any of the other elements, I will obtain the same result. So I will use multiplication then. That is why the operation is not addition, but multiplication. So, good. The operation is figured out. What about the identity? Well, we just figured out that the identity is the element that changes nothing when multiplied with any of the other elements. That is 1. So the identity is 1. What about the inverses now? We can't have a group without inverses, can't we? No, we need to have inverses. So let's find an inverse for 5. What is an element that if I multiply to 5, I get back the identity element 1? So 5 times what gives me back 1 bar. Well, to see that, we'll have to try and multiply 5 with some elements in the group to see if we get back 1. So 5 times 7, that's 35. But what is 35 congruent to mod 12? To see that, we need to divide 35 by 12 and see what the remainder is. If the remainder is 1, well, that's just 1 bar. We're done. So 35 divided by 12 gives you 2 with a remainder of 11. Clearly not 1. So it's not 7. Is it 11? Their product gives 55. But does it really give 1 when you divide it by 12? Does it really give 1 as a remainder? Let's see. So 12 times 4 is 48. And their difference is 7, not 1. What else is there? Well, there is 5 itself. So if we multiply 5 by itself, we get back 25. And what is 25 modulo 12? 25 divided by 12, it's 2 with a remainder of 1. We're done. That is the remainder we wanted. So 5 is its own inverse. Great, right? So we have found the inverse of 5. What about 7? Is it the inverse of 7? Is it 7? 7 times 7 is 49. You divide 49 by 12, you get 48 with a remainder of 1. So it is an inverse of itself. 11. Is it the same thing? 11 times 11 is 121. You divide 121 by 12. What do you get? You get 10, remainder 1. So 11 is also its own inverse. And 1, well, 1 times 1 is 1. So 1 is also its own inverse. And so every element in this group is its own inverse. And that, ladies and gentlemen, is a coincidence. Not all groups have this property. So in this case, the inverse is the multiplicative inverse. That gives 1. So we would call it a to the power minus 1. Of course, that notation just means the number that, when multiplied by our element, gives back 1 bar. Great. That is our group, multiplicative group of the integers modulo n coprime to n with this example. Our last and not least, certainly not least, example of groups is a direct product of groups. Let's say we have two groups A and B. Okay, so we have the group A. We need to have an operation. Let's call it star A. And the group B has its own operation called star B. So these are two different sets, two different operations. Very general. They could be any sort of group that we want. They could be even the groups that we've talked about earlier. So we have two groups. What can we do with two groups? Well, we can take their direct product. So the direct product A cross B is defined to be all the elements A comma B, where A is in big A and B is in big B. So all what we're doing is we're taking a vector, a combination of both elements, one from A and one from B. All the possible combinations from these two sets. And what is the operation, you may ask? What is the star of A cross B? Well, the star of A cross B is a very natural star. It takes the operation of A and the operation of B. So in the left component, we apply the operation of A, and in the right component, we apply the operation of B. So that, for example, if A1 and A2 is in, if A1 and B1 is in A cross B, and A2 and B2 are in A cross B as well, then let's apply the operation of these two elements together. A1 B1, A2 B2 gives you A1 operating with for A on A2 and B1 operating with the operation of B on B2. Perfectly valid operation. So this operation is the combination of both operations of A and B. What about the identity? The same way we combined both operations, can't we combine the identities as well? Because we know that A and B are groups, so they must have identities and they must have all the group stuff. So we take the identity, so let's call the identity E. So it will be E of A and E of B, the identity from A and the identity of B. So that is our identity. And we're gonna test that. Let's test it. So EA, EB operating on any element AB gives you EA star A on A and EB star B on B. We will treat each component separately. So EA star A, by definition of EA, gives you A. EB star B, by definition of EB, gives you B. That means that this element absolutely has no effect on AB. It gives the same AB. So it is the identity, in fact. Lastly, the inverses, just like the identity, just like the operation, we will naturally get the inverses of both the element from A and from B. So we get the A inverse, B inverse, star AB. That will give you A inverse star A, B inverse star B, B, and of course, by definition of both of them separately, we get EA and EB. And that, ladies and gentlemen, is the group of direct product of two groups. It is worth noting that for all the previous examples, associativity is a must because we are in a group. So here, both groups are associative. So of course, their direct product has to be associative. I can leave that to you as an exercise to prove that. The groups I've mentioned earlier, the integers and the integers modulo n and the ones coprime are all associative because addition and multiplication are associative by nature. So that concludes the lesson for today. If this is the first time watching, I really appreciate it. Please follow more. I will be uploading the rest of the lessons of this course very, very soon because I really would like to share what a wonderful subject algebra and particular group theory is with everyone. So thank you very much and have a good rest of your day. Bye-bye.